All right. Hello. How are you doing? I hope class is going well for you. Here we are on chapter 5, moving right along. We're not halfway done yet with the class tip chapters, but we still got a few more major topics, and this is one of them. Normal distributions are like the foundation of statistics. Normal distributions help us with testing all of chapter 6, all of chapter 7, all of chapter 8. You have to understand what a normal distribution is. When I was a student in statistics, my instructor wore a shirt that said it had a normal distribution curve in, and she said, "What part of normal don't you understand?" All the time. And I don't think I knew what normal meant until I did some studying. I watched a YouTube video, try to figure some stuff out on my own. But I'm going to attempt to explain normal distributions. You might have to watch this video a couple times or find other videos of people you like. I don't know. Hopefully you like me. I don't know. Normal distributions. So this is a normal distribution curve. And what it tells us, it gives us the area under the curve is 100% of all values. Now this axis here is called the x-axis. And usually we define the x-axis as a variable. So I gave some examples of populations that are approximately normally distributed right over here. Speed on the freeway. So if you're driving down the freeway, some cars drive slow. Those cars would be represented by the area over here. Some cars drive fast. That's here over here. But most cars drive in the middle, in this area in the middle. Okay. Test scores. Again, some people score high, some people score low, but most are average. Miles per gallon, anything human, height, weight, um, IQ, cholesterol, blood pressure, things like that are approximately normally distributed. And anything is manufactured. If you go to the store and you buy any product, it says in a water bottle, this water bottle has 16.9 ounces of water in it. Well, is it exactly 16.9000 ounces? And the answer is probably not. So within every everything that's measured, yogurt, candy, cereal, and cereal box, there's an amount or a weight on the side of those products. And with a standard deviation, there's some variation in each of those products. So we can use the normal distribution curve to make those decisions. So we have right in the middle, this is the halfway point, and wow, that's terrible. Can I undo that? Right in the middle is the mean. So the mean is what we're going to measure as a population mean. Come on. So the mean is measured as mu. So population, we're measuring population parameters when we're talking about this. We could use a statistics mean, which is X bar, which we've seen before. In this case, we're going to use a population mean, which is mu, and a population standard deviation, which is sigma. Now, I don't know why it's so hard for students to call it sigma. Everyone calls it the O thingy or the circle thingy. Okay. So these are two measures of population statistics. Okay. So if I talking about speed on the freeway, if the average speed of all vehicles on the freeway on the 101 freeway is 65 miles per hour, that's average. And you drive down the freeway at 70 miles per hour, that's not average speed. That's above average speed. So that speed is over here somewhere. So if average is in the middle, above average would be 70 miles per hour. Okay. Well, if you drive 80 miles per hour, well, now we're talking farther away from 65. Can you drive 90 miles an hour on the freeway? Yes. But this area right over here represents a small portion of people that drive 90 miles per hour. So if the mean is 65, that's average speed on the freeway, with a standard deviation of 5 miles per hour, we want to know what is normal driving speed. So 65 in the middle. Where this graph turns down and turns back up is called an inflection point. So right about here, right about 2/3 of the way up this line, about 2/3 of the way right across here on the inflection point. And on the left inflection point is where we put our first standard deviation. So I'll put a line there and put a line over here. So the area in between, using the empirical rule, remember the 68, 95, 99.7 rule. I'm just going to go over that real quick. That's one deviation. And then at the bottom of the curve is 2 deviations. So I'm just going to add and subtract 5 each time. We did this previously. So add 5 to 65, add 5 to 70, 75. So I'm adding 5. Now I'm going to subtract 5. Why 5? Because 5 is the given standard deviation of all cars and trucks and RVs and their speed on the freeway. So we want to know what is the speed of most cars. Most cars drive between 55 and 75 miles per hour. That's 95% of your vehicles on the freeway. Okay, including diesel trucks, RVs, trucks towing trailers. Those cars are driving slow. There's not a lot of them, but they slow everyone down, right? Average speed, okay? Average speed, 65, right in the middle. Normal speed, 55 to 75. Can you drive faster than 75? Again, that's a yes. That'd be 80. That'd be over here, or 90. I saw a car pass me. It must have been going 110 miles an hour. Okay, is it possible? How many standard deviations above average is that? Well, that's where we get into that z-score formula. So what I'm going to do is calculate the z-score. So z-score will tell me how far above average are we. So x is a single value, mu is given, standard deviation is given. So we're going to subtract these two numbers and then divide. What that does, it places where our speed is at on the freeway. For example, if I drive 65 miles per hour on the freeway, I want to know what percentile is that. Okay, so we're going to jump from a x value, these are all x values, these are speeds, to a z-score. So so this is x, then we're going to jump to a z-score. Here's a z-score of 0, here's a z-score of 1, here's a z-score of 2. Go left, below average, -1, -2. So again, if I drive 65 miles per hour, I'm going to find that z-score. Z equals 65, which is x is my speed on the freeway. That's how fast I drive. Well, that's average speed. So I'm going to do the math. 65, take away 65 is obviously 0. That's a z-score of 0. A z-score of 0 is what percentile? So the big focus here on 5.1 normal distributions is going from z-score to a percentile. This is the 50th percentile. What does that mean? That means 65 miles per hour is the halfway point. The area from here to the left is 50%, and the area from here to the right is 50%. It's right in the middle. What if you drive exactly 65? What percent of drivers are going exactly 65? That would be a whole different question. Okay, so when we say 65 miles per hour, we're saying 65 or less. Okay, so we always cover a left tail area. So find the z-score. I found the z-score by using the z-score formula. And then from there, I go to a percentile. That's all we're going to focus on right now. I'm not so worried about these x values. That is going to come a little bit later when we move on to 5.2. But for right now, we're just going to translate from z-score to a percentile. So again, going back to this example, if I drive 65, z-score is 0, 50 percentile. What if you drive 70 miles per hour? That's a z-score of 1. What percentile is that? So z equals, how do I know it's 1? I'm going to do the math. Z equals 70 minus the mean, which is 65. And you're already probably done it in your head. 5 divided by 5 equals 1. Okay, now one point of emphasis, make sure you're careful. If you just punch this in your calculator, if you press on your calculator right now, you're going to press 70 minus 65 divided by 5. I got 57. 57. Okay, what did the calculator do? The calculator did division first. The calculator divides 65 by 5, and it's 70 minus that. So 70 take away 13. Well, the calculator does order of operations. If you're going to use a calculator, I would subtract first, get that number, and then divide by 5. Or you could just put parentheses around the numerator, and that gives us the 1. So a z-score of 1 is what percentile? What percentile is that? I don't know. Well, there has to be a way to do this. So what we're going to do is find z-scores from here, from 1, and we're going to find the area. We're going to find the area to the left of 1. So we're going to find all this area over here. If the area to the left of 65 is 50%, what's the area to the left of 1 standard deviation? In other words, 70 miles per hour or less. So what we got to do is use table 4, appendix B. It's called appendix B, page A16 and A17. Now I have my book here. I bookmark one page in my statistics book, and that bookmark is A16 and A17. Big, huge table. Big, huge table. Okay. We're going to learn how to use this table right now. So what I'm going to do is go to a z-score of 1. I'm going to go to a z-score of 1. So I'm looking at the table. Let me, we'll use the calculator in a little bit, but I want to get familiar with the table. Down the left side, or A16 are all negative z-scores. A17 are all positive z-scores. Down the left side, okay, it says z, and the very first number is 0.0. I'm going to go down the table until I get to 1.0. And then I'm going to go across until I get to 0, 0. Okay, so I'm just kind of doing a replica of the table. So when I go over 1.00, the number that comes here is my percentile, 0.8413. That number falls, that represents 70 miles per hour or less. So to answer the question, what percent of cars on the freeway are driving 70 miles per hour or less? That's about 84% of cars on the freeway. 0.8413. How about 2 standard deviations? Now I'm going to go to 2.0. So let's go all the way down to 2.00 and see what number we find. 2.00, I got 0.9772. 0.9772 is the 97th percentile. Now we use this because a lot of people will say, okay, percentile. What percentile are you in? The top 1%, that's the 99th percentile. The top 10%, is the 90th percentile. We'll get the percentiles and using those measurements when we get to 5.3. But right now we're just saying this value or less. Okay. How about -1? That's about 0.16. I'll be more exact. I'll put all these numbers on there. 0.8413. So I know what this number is. 100 minus 0.8413 is 0.1587. And if you don't believe me, go into a z-score of -1. Wait, that's on A16. Go to A16. Go, starts at the bottom. This goes back. A16 is backwards. Okay, it's backwards. It's kind of confusing. I'm going to go up to -1.0, but look at the number right next to it, 0.1379. That's not it. That's -1.09, a z-score of 1.09. I got to go all the way to the interior, -1.00. Hopefully you're following along on the standard normal table. You could always Google standard normal table and you'll find it's the same no matter what, if you find it in Google or if you find it in the book. 0.1587. Okay, so these percentiles are really useful. So we're just using table 4. All we're doing here in 5.1 is finding percentiles using the table. So I'm going to find a couple of percentiles. I'm going to give a couple of examples. So there, right here, it says find a left tail area, find a right tail area, and an in-between area. So I'm going to give examples of that. I want to find the area left of a z-score. Z equals, let's go 1.27. So let's say speed on the freeway. If you're driving 72 miles per hour, that's your speed. Oh, I have a friend. If I drive 72 miles per hour, I won't get pulled over because my friend's a police officer and the police officers don't pull over someone drives 72 miles per hour. Well, I calculate the z-score, and let's just say I got a 1.27 for that z-score. What percentile represents 1.27? The area to the left of z equals 1.27 is what? So I'm going to go to z equals 1.2. I go down to 1.2. And I go across until at the top, I see 0.07. So I'm just taking a snippet. And this is in the book, in the example as well. There's several examples about this. So I go to 1.2 and 0.07. 1.2 plus 0.07 represents 1.27. So I'm just going to use the value that falls in here. And I'm going to look it up right now. 1.27, 0.8980. Wow, that's pretty close to 90%. That's almost the top 10%. 0.8980. So the answer to this question, find the area to the left of z equals 1.27. I'm not going to put an equal sign here to represent z equals 1.27, which equals 0.898. Okay, I like to just say that 0.1 z equals 1.27 is, instead of putting an equal sign because it's confusing if you do it like that, 0.898. And this again represents the area. So 72 right over here. 72 is between 70 and 75 miles per hour. That's the z-score. So I got 72 right here. 72. That represents, I'm drawing the arrow, 1.27, which represents 0.898 as a percentile. Okay, so this is one of the things we do with normal distributions. Go from an x value. It could be average height. Okay, I'm 5 feet 5 inches. Below average height, I'm pretty short. Okay, but I have normal height. I'm within 2 standard deviations of the mean. You can talk about any x value you want. So we go from x value to z-score to percentile. How do we get the z-score? We do the z-score calculation. How do we get the percentile? We use the table. to get these values. I'm going to show you some notation, and it pops up in 5.1. The notation goes like this. And if you're in the fifth edition, I'm sorry, the fifth edition, the eighth edition of the book, it is on page 5.1. I should have bookmarked this page as well. If you look at page 245, there's a whole bunch of problems that use this notation, P and then Z. Find a Z-score that's less than 1.27. I like this notation because then I could put equals. Find the capital P. Remember, we learned probability. The probability, and you put the event in the parentheses sign. The probability Z is less than 1.27 is, well, now I could use equal sign because I have those parentheses there, 0.898. And that's the Z-score. So again, relating it to speed, 72 miles an hour represents 1.27, which represents 0.898. I didn't actually calculate the Z-score. I could have really quickly, but I just estimated 7 divided by 5. It's 1.2. Yeah, I was off a little bit. Oh, well. That's a left tail area. I can look up another left tail area. Let's go area to the left. Area left of Z equals, let's do a negative 0.68. Go ahead to your table. Again, you should be able to flip back to your table real quick. If you bookmark, I just fold over the top corner of the page. Go to Z equals negative 1.28. All right, what did I just say? I'm sorry. Look up Z equals negative 0.68. Negative 0.6. Go all the way down near the bottom, 0.6. Go over 2 spaces. At the top, it's 0.8. You kind of got to use your finger or maybe a ruler to guide. 0.2483. 24.8th percentile. All right. So z-score of negative 0.68. Here's a z-score of 0. Here's a z-score of negative 1. So I would say that's probably somewhere between 60 and 65 miles per hour on the freeway. Probably closer to negative 1, somewhere like 62 miles per hour on the freeway, about. Those are all called left tail areas. Left tail areas. Find the area to the left of these values. We also have right tail areas. If you're asked to find a right tail area, what are you going to do? Okay. Let me get rid of this little guy right here. There we go. All right. So what's a right tail area? Okay. So this is finding the probability of someone going over, let's say, above 70 miles per hour. So here's 70 miles per hour right here. This is the use of finding the right tail area. 70 or more. Okay, so I want to find this area over here. It's obviously below 0.5. So what percent of cars on the freeway are driving 70 miles per hour or more? Okay, right now we say 70 or more than 70. They kind of have the same meaning right now. Later on, we'll get an exact measurement of those two differences. Find the probability of driving above 70 miles per hour. Okay. Well, that's a z-score of 1. I looked up 1 in the table. I got 0.8413. Well, that's not the answer. Remember, the 70 miles per hour or less was 0.8413. So if I'm asking this question, I would say find the area to the right of z equals 1. Find the area to the right of z equals 1. Which is the same as saying find the probability of driving greater than 70 miles per hour. I might as well just show that. I could use an x value. Again, we're going to get to this a little later in 5.2. We'll spend a lot more time and do several examples on the probability of driving 70 miles per hour or more. And sometimes if I say 70 or more than 70, again, two different meanings. If I say 70 or more, we would do something like that. Okay. They have similar meanings, but we'll get to that 5.2. Anyhow, I translate this to a z-score. On the probability of z being greater than 1. How did I get 1? 70, take away 65, divided by 5 is 1. So x being 70, what does that translate to? So it's translation, like one language to another. I'm translating from the language of x, speed, to the language of z, to the language of percentile. So we jump back and forth between all three of these things. And the way to transform from one to another is called the z-score formula. Transform to percentile, got to use the table. Okay, let's stick with z is greater than 1. So I find the area to the left and subtract 1, subtract from 1, and that'll give me the area to the right. So what I'm going to do is go 100%. The area under the entire curve is 100%. Z is less than 1. Notice the sign changed. Okay. The probability z is greater than 1 is what I'm trying to find. So find the probability z is less than 1, 0.8413, and subtract that from 1. 0.8413. So when I do 1 minus 0.8413, I get 0.1587. What does that mean? 0.1587. 0.1587 is a percentile. Or not, I'm sorry, not a percentile, but a percentage. Left tail areas are called percentiles. Right tail and in between areas are called percentages. We're finding areas in between. So 15.8% of cars drive 70 miles per hour or more. About, it's an approximation. We're approximating, we're estimating. And this is population values. It's not necessarily true at all times, but 70 miles per hour or more, about 15% of cars will drive that fast, vehicles. So that's, again, an application of using z-score and right tail areas. There's cool pictures of this. I think they're cool. I don't know. I'm a math person, but you might not think they're cool. Page 243, 17 through 22. There's some pictures in shaded blue region. The shading in the problem sets show if it's shaded left, you find the area to the left. If it's shaded right, you find the area to the right. Subtract from 1. It's in between. Then we've got to find 2 areas and subtract those. Okay, here's a really cool shortcut. Okay, I'm all about the shortcuts. Like using this eraser instead of erasing the whole thing, just knocks all that stuff out. Shortcut. All right. Instead of starting over. What I'm going to do now is use the calculator. On the calculator. Hopefully you have a calculator or a calculator app. If you didn't have one by now, you get one. So on the calculator, we're going to use a function called Normalcdf. We're going to enter a lower bound. We're going to enter an upper bound. We're going to enter a mean. And we're going to enter a standard deviation. there. There we go. How do we get to normal CDF? Okay, good question. Like, what is it? We're going to a new place. Oh, you know what? We've been there before. Binomial distribution, geometric distribution, Poisson distribution. They're under distributions, normal distribution, second vars. So second on the calculator and VARS. And above that, it says DISTR. And you can see when you go to second vars, number 2 is normal distribution. There's a PDF and CDF. I mentioned find the probability of driving exactly 65 miles per hour. That's what the PDF is used for. We'll get to that later in 5.4. But CDF is cumulative, just like binomial, cumulative. We're going to find a total area. This may not show on your calculator. Your calculator may show lower bound, upper bound, mean standard deviation vertically, and then it'll say paste, and it'll paste it up to your screen. So I'm going to go through and let's do area left of z equals 1.27. I'm going to do a left tail area, normal CDF. I'm going to use a really small number. In the textbook, they use negative 1,000 or negative 10,000, or I think it's already automatically set by default. If you have Stat Wizard, it says negative 1 E99. Okay. Page 241, it shows the normal CDF calculator function, how to do it in the calculator. So we go negative 100, go to 1.27, comma, 0, comma 1. Okay, what's that? Okay, what I just did right there, I found in terms of z-scores, I'm looking only at z-score. I'm not talking about like speed on the freeway right now. I'm finding in terms of z-score, I'm going to use a really small z-score, like negative 100. I'm going to go all the way up to 1.27, which was right here. The mean is 0. 0 is in the middle. Standard deviation is 1. So when I do that, I should get a percentile. Oh, common mistake. A lot of people will use minus 100. Okay, it's negative 100. The negative sign is at the very bottom. The minus sign is on the far right. Negative 100, comma, 1.27, comma, 0, comma, 1. If you use minus, the minus sign, you will get an error. So this equals 0.89795766193. Okay, so obviously the calculator is a little more accurate than the table in the book. But if we went to 8 decimal places with the table in the book would be like 4 pages, like the Poisson table. 0.898. Ooh, that's really close to 0.898. Check it out. There it is. 0.898. Same thing. So there you go. For you calculator people. Okay, some people are still scared of the calculator. Treat it like a cell phone, okay? It's like you had it's a new app, okay? Learn it, use it, practice it. It'll be fine. Let's do negative 0.68. Let's do this one. What would I put in there? So let's see here. Use a really small number, normal CDF, small number, negative 100, comma, negative 0.68, comma, 0, comma, 1. Yeah. All right, so we should get 0.2483 or something close to that. What if you put negative 1,000 right here instead of negative 100? You'll get the same answer. What if you put negative 10? These are all z-scores. What if you put -1, comma, -1.68? That'll give you a little area. That'll give you a sliver of area in between these two numbers. Oh, speaking of in between two numbers, this is why I did this. The in between areas, I didn't do it by hand. If you want to do the in between areas by hand, that's fine and dandy. It's a whole lot of fun. But finding in between areas with z-scores, our book doesn't really even go into it. Okay, we don't really have an in between areas. There's one example, example 6. Find the area between z equals -1.5 and z equals 1.25. We might as well look at that one, example 6. So I'm going to write it right over here. In between areas, in between, I'm going to use the notation probability z is in between -1.5. So let's use notation. They didn't really do it for this problem. And 1.25. Apologize, I got a loud barking dog over there. Keeps us all entertained. Okay, so that's the notation. This is the area in between -1.5 and +1.25. Again, page 241, example 6. They showed us a picture of what it looks like. Very, very similar to some of the problems that you're going to see. In order to do it by hand, I got to find the area less than -1.5, which is 0.0668. You can see that in the picture. And find the area to the left of 1.25, which is 0.8944. To find the area in between, I got to subtract those two areas. That's doing it by hand. Kind of confusing. I'll show you the notation. Probability z is less than 1.25. And I'm using my mouse here to try to, my keyboard mouse. That's why it sucks. Sorry, my next video is I'm gonna use an app. Okay, I'm gonna get an app. I'm gonna use my iPad and do it right. You call me Khan Academy. That's what he does. Wait, why did I put 1.25? Find the area to the left of 1.5. Apologies. 1.5. Wait, let me look at this again. Yes, I had it right. 1.25 and -1.5. I don't know why I could just confuse myself just now. All right, there you go. So this area is, I'm going to look up 1.25. That's 0.8944. Take away 0.0668. That's the area to the left of -1.5. 0.0668. And that equates to 0.8276. 0.82. That's the answer. The area in between these two numbers is 0.8276. And why would I need to find an in-between value? -1.5, that's like right here. That would be, let me get rid of this scribble over here. So -1.5, that's like a speed of 57.5 miles per hour or 58 miles per hour, somewhere in there. 1.25, that's like, again, 72 miles per hour. Find the probability or what percent of cars drive between 57 and 72 miles per hour. It's a question. I use standard normal distributions to answer the question. That answer is about 82% of cars drive those speeds. Now, here's the cool thing. I could have done it all on the calculator. And there's a picture of it right there. Normal CDF, lower bound. I like in between areas. The calculator is really dandy to use. Negative 1.5. Go up to positive 1.25. The mean, excuse me, is 0. Standard deviation is 1. Oh, I heard the fireworks. Come on, people. It's September. We don't need fireworks. And that should give us 0.8276. So now, your turn. Please go and do some practice. If you have questions, send me an email or meet me on Zoom and the office hours, and everything will be fine. Sound good? Go for it. Oh, you want to just go on to 5.2? Sounds good. Let's go on to 5.2. Let's keep it rolling. Well, we pretty much covered a lot of 5.2. Speed on the freeway. Speed on the freeway. Practice drawing that curve. Let's do an different example than speed on the freeway. Let's do average. We'll do a couple of examples here. 0, -1, -2, +1, about +2. That normal curve is pretty terrible, but it's okay. Let's talk about IQ. IQ is a measurement of knowledge, brain capacity. Like, what do you know? Average IQ is about 110 with a standard deviation of about 15. So I would write that up here. This is the given. The mean of the population, all people, the measurement of their intellectual ability is about 110. Standard deviation is about 15. Okay, don't Google it and then send me a text and be like, hey, you're wrong. Okay, I'm just estimating what these values are. And they change year after year after year. Okay, lots of things change over time. So I'm just going to add one deviation. I got 110 plus 15, 125, 140. How'd I get that? I added 15 twice. Whenever you're dealing with normal distribution problems, I always say draw the curve. When in doubt, draw it out. When in doubt, draw it out. So you have a picture. Everyone's like, I'm a visual learner. I need pictures. That's what we spent all of chapter 2 drawing pictures, stem and leaf plots, box and whisker plots. We drew dot plots, pie charts, because a lot of people need pictures. There's a picture representing what's going on with IQ. Average IQ is 110. That's the 50th percentile. That's a z-score of 0. This is a z-score of 1. So you show up and you say, I'm cool, I'm good, I don't need to do any of this. I got an IQ of 150. Oh, that's cool. You got an IQ of 150. So smart. Okay. What z-score is that? Well, obviously it's above 2. 150, I'm going to calculate the z-score. That's where the z-score formula comes from. 150 minus the mean divided by 15. So I got 40 divided by 15. And I'm just going to, you saw on the table, the z-scores were always rounded to the nearest hundredth of a decimal place. But if you do it on the calculator, it's not going to round. So 15 goes into 40, 2.67 times, 7 repeating. If you divide those two numbers. Oh, this is a 2, by the way. Notice I put, with z's, I always put a line through it so I don't distract between 2 and z. Just a habit of mine. 2.67. What z-score is that? Oh, let's go to the table. A16, A17. I'm gonna look up 2.67. Go down to 2.6. Go across to 0.7. 0.9962. 0.9962. We're talking percentile. What does that mean? 0.9962 percentile. So this person with an IQ that showed up to our class that says, I have an IQ of 150. Actually, I had a student there. He came in, he didn't have a calculator. He's like, I can't afford a calculator. We'll go rent one for $10. I can't. He did everything by hand. He found standard deviation by hand. I was like, dude, you're a genius. It smelled like weed. It was terrible. Yeah, it was bad. But he was really smart. He's in the 99th percentile, the 99.62 percentile with an IQ of 150, measured that really high. Okay. 150 minus 110 divided by 15 measures those things out. Okay. 150 way over here. Here's 150. The area to the left of 150 is the 99th percentile. There we go. It's calculating z-score. Go from z-score to a percentile. You always take this state test. When you take the state test, they give you state test scores or state test results. So usually the state test scores, I'll use my kid's test score as an example from what I just saw from the report card. It said that the national average, they didn't give us a standard deviation, I don't recall, but I remember seeing the national average was 190. Then they gave the district average, they gave the school average, and then they gave your student's score. So it had like a minimum value and then a maximum value. It was like you range. We'll talk about confidence intervals later. Your child ranges between 180 and 200. Okay, so I'm assuming that is measuring standard deviation. If the average test score is 190, I don't know what the scale is. I'm assuming the standard deviation is about 10. If my daughter comes in and she scores 197 on her state test, I get the report card. It says 197. What does that mean? Oh, and then there's percentile on there. Read your kid's report card. You might see it. Or your old report cards. Go dig them out. So 197 right over here. That's not a z-score of 1. A little bit less than 1. Let's calculate that z-score. How do we do that? Oh, we use z-score formula. Z equals 190. Oops, not 190. In fact, I should change what I'm doing right here. So I've changed my mean to be 190 and my standard deviation to be 10. So I'm going to use those values. So I got a 197 is my child's test score minus the mean. Again, I'm trying to figure out what percentile are they in. Oh, you're in the 80th percentile. Well, I know it's above average, above the 50th percentile. Do the math. 7 divided by 10. Oh, I don't need a calculator for that. 7/10. 0.7. I go to the table. I go to 0.70. I got 0.758. Okay, this 0.7 is a z-score. The 0.758, 0.7 is 0.758. This is why I like the notation. I like the P notation. So again, going back to that P notation, probability X, which is your IQ, probability X is less than 150. What's that going to be? Well, that's equals to a z-score. So I transformed it into z-score. So I'm going to stay with the P notation. Already found that z-score. So 150 minus 110 divided by 15, 2.67. Well, what's that going to be? What's a z-score of 2.67? That is 0.9962, or I could write it as a percentile. Sweet. 99th percentile. Top 1%. Okay, if you got an IQ of 150. What if you have a test score of, we're getting there. What's probability someone scores a 197 with a mean of 190? Well, I'm going to translate that to a z-score. Again, the z-score formula translates for us to another language of the z-score. Then again, I need to translate that into a percentile. Don't confuse z-score and percentile. They are different things. That looks like a percentile, but it's a z-score. Okay, so that is, I'll put equals over here. That is 0.758, or the 75th percentile. And what's the area right used for in this case? My daughter is in the 75th percentile compared to the national average on the test, the top 75%. Okay. Well, there's about 25% or 24% of students that have higher test scores than her compared to the national average. Okay, that's the meaning of greater than in this case. Okay, here's a really cool option. We could skip all of this math. We could skip the z-score formula because the calculator does it for us. Again, we're in 5.2 and we're finding areas. They got ACT score, SAT score, pregnancy length, blood cell count, heights of women, heights of men, MCAT scores. All these things are represented in 5.2. The calculator input is on page 248 in the example, or in the 8th edition of the book, page 248. So we're going to do normal CDF. I want to figure out probability X is 150. So again, I'm going to do normal CDF 150, comma, or I'm sorry, I need to use a really small number. I'm going to go up to 150. Put in the mean. The mean was 110. This is IQ. Standard deviation was 15. Again, this is, I moved it. Well, let me move. Okay, this should give us the 0.9962. This should give us the 0.9962. What if you want to know the top 1%? Okay, if you have an IQ of, what's the probability of being 150 or more? The area to the right of this. I would use a different normal CDF. I didn't really address that in 5.1. Find the probability. So a question would be like this. Find the probability someone has an IQ greater than 150. What is the probability someone has an IQ greater than 150? Okay, so now I'm going to use notation here. Probability. Okay, remember X is IQ. Probability X is greater than 150. So what do I got to do? I got to find that 150 as a z-score. Okay, we did that, 2.67. Translate it to a percentile, 0.9962. Then do 1 minus 0.9962. Why do I got to do that? Because the area under the curve is 100%. And the math that I got to do is this. Probability X is less than 150 is 0.9962. So I'm going to do 1 minus 0.9962. So that's going to give me point, maybe I got to do it in my calculator. I don't want to screw it up. 38, something like that. 1 minus 0.9962, 0.0038, just like I thought. 0.0038. Ooh. All right, that's area to the right. All right, here's again the best thing about using a calculator. I can find right tail areas as well, just as easy. Normal CDF. Now I'm going to use that 150 is the lower bound. 150. I'm going to use a really big number. I'm not going to use 100 because if the mean is 110, this would say find the probability somebody has an IQ greater than 150 but less than 100. Okay, that doesn't make sense. So I need an IQ much greater than 150. I'm going to do like 200 or 300 or 1,000. Okay, let's use 1,000. The mean IQ is 110. Standard deviation for IQ was 15. And that should give me the 0.0038. Normal CDF. Okay, let's go to this example of test scores. Normal CDF. Do negative 100. And let's go all the way up to a X value of 197 and a mean of 190 and a standard deviation of 10. That should give me that 0.758. But again, the calculator is going to be a little more accurate. And this is why the calculator is really useful, really good for shortcut, right? So we don't have to calculate the whole Z-score. We don't have to do all that mess. Find the area to the right. What percent of students scored higher than a 197? Okay. Well, if the area to the left of, again, this is 197 right here. If this area is 0.758, this area is how do I write it? 0.758. That's the area to the left. On the area to the right, I subtract from 1. That'll give you the area from here. Subtract from 1. 1 minus 0.758, 0.242. This area under the curve is 0.242. And if I do normal CDF, it's going to give me that area. Something happened there. I shrunk my screen. Okay. So I do normal CDF. I would find the area to the right. Real quick, I'm going to do normal CDF. And I need 197 to be a lower bound. 197. And I'm going to use a big number, not 100. Use a really big number, not 200. I'm going to use 1,000. The mean is 190. Standard deviation is 10. So this works for any population that's approximately normally distributed. So again, this one should give us 0.758. The area to the left of 197. And this one should give us the area to the right. Let me be sure 1 minus 0.758, 0.242. Yep. Equals 0.242. Yeah. All right. Good luck. And again, questions, let me know. Have a good one.